Welcome students to the next video lecture of digital communication. So today we will start MRE signaling techniques. So in the last video you watched I was talking about QPSK. So you can have four signals corresponding to four different combinations of a 2-bit symbol. Okay, so in case of your QPSK, let's say you had so QPSK, it had four signals because you had a 2-bit symbol, and since you have a 2-bit symbol, you had 2 to the power 2 possible combinations. Of how these bits are arranged in the symbol, and out of this 2 to the power 2 combinations, which is 4, you are sending one of them at a time, and for each combination you have one signal mapped to the bit combinations that you have. So you had 4 signals. So extending these concepts, you can have, let's say, if you have a 3-bit symbol, then you have, let's say, 2 to the power 3 or 8 combinations, and then you can have 8 signals. So in general, you can have m signals, and you can have, let's say, lambda bits per symbol, and you can have corresponding to that 2 to the power lambda signals. So if your m is equal to 2 to the power lambda, where your lambda is greater than 2, then you can call it as a general MRE signaling. Okay, for lambda equal to 2, you call it QPSK. So why would we would do this type of signaling? So there are benefits for sure by doing MRE signaling methods, and the first benefit that you can think of right now, let's say if I stop here and I don't proceed any further right now, probably if you take a few seconds to think about one of the benefits, you can probably think of it from the concepts you have learned so far in this semester, both in digital communication and your wireless communication. So if you recall the Nyquist channel capacity formula, so you had the capacity of a channel defined by the bandwidth of the channel times the log of log to the base 2 of m, where m is your number of signal levels. So here this m and this m are the same. So basically, if you are doing binary, then this m is equal to 2, and then you just have c equal to b. Whereas if you do higher m, let's say m equal to 4, then you have c equal to twice of b. If you have m equal to 8, you can have c equal to thrice of b. So you are gaining in terms of the capacity of the communication channel. Okay, so with the same fixed bandwidth, if you are increasing the number of levels that you can um, transmit, then you are gaining in terms of the capacity of the channel. So, so the gain in bandwidth is accomplished at the expense of the error performance. Okay, so you can see that for QPSK, um, there are 4 signals, so you are gaining in terms of the bandwidth, but the error performance is is low. Okay, when you have more number of signals, we will see shortly why is that. Okay, um, so this thing I already said, that if your bit stream is grouped into lambda bits, then the number of bit patterns is 2 to the power lambda, and that is equal to your m, the number of signals. Okay, and the symbol transmission rate is given by 1 over the symbol time, and that is 1 over lambda times TB, the bit time. So if you are having lambda symbols, sorry, lambda bits per symbol, then each of these bits have a bit duration TB. So the total symbol duration is lambda times TB. Okay, so 1 over TS is 1 over lambda times TB, and 1 over TB is your bit rate. Okay, so RB. So basically, the symbol transmission rate is RB divided by lambda. So, so therefore, your bandwidth saving of 1 by lambda is achieved. So what bandwidth you required for transmitting a binary signal, you can achieve that within 1 over lambda of that same bandwidth. Okay, so so basically, this is the advantage. Okay, and this is also related to this fact. Okay, so your um, your effective bandwidth that the signal is occupying is getting reduced because of your your MRE uh, signaling technique. Okay. So if we now extend this concept of MRE signaling to everything that we have learned so far for binary and for QPSK, which is a special case of m equal to 4, then you will see that the same concepts can be applied. So optimum receiver for MRE signaling, nothing much change. You have the same structure. Here you have SIT, which is the ith signal. So in case of MRE, you have M signals from S1, S2 to SM. Okay, and you can represent them generally by SI, and then the received signal will be the ith signal plus noise, and then you do the same analysis. Okay, so you can represent any signal SIT in the orthonormal um, in the signal space spanned by the orthonormal basis set phi n t, and you can represent the ith signal in terms of the orthonormal basis functions like this. So in case of binary, you were saying S1 t was equal to S11 times phi 1 t plus S11 1 2 times phi 2t, right? So here also you can do the same. So you can, if you have m signals and n basis functions, then you can represent all the m signals in terms of the basis functions, and then the received signal will be the ith signal plus the noise, and then you have the components of the received signal r1, r2, rn, etc. And you in this case need to partition the signal space, the n dimensional space, into m regions. So earlier in case of binary, you were partitioning the two dimensional space into r1 and r2 into two regions. Okay, in case of your QPSK, you were partitioning into four regions. So R1, R2, R3, and this one would be R4. Okay. So in this case of MRE also, you can partition either a n dimensional space or a two dimensional space, whatever. So if let's say your m signals can be represented by two dimensions, which means only phi 1 and phi 2 is enough to represent all the m signals, then you can represent them in the two dimensional space, and in that case you can divide the two dimensional space into m regions. Okay, but generally speaking, you can divide the n dimensional space into m regions. Okay, so so here is the same concept. So just for the sake of your understanding, imagine that this n is 2, so you are seeing a 2D space here, and you can divide this 2D space into m regions, so r1, r2 up to rm, and if your received signal with all its components falls into one of these regions, then you take a decision in the favor of that particular signal. So if R1 is the region where your received signal is falling, then you choose S1T. If R2 is the region where your received signal is falling, then you choose S2T. Similarly, if your received signal is in the region RM, then you choose SMT. Okay. So the optimum receiver also in this case is a minimum distance receiver. You can apply the same logic as you did for binary and QPSK, and you can deduce that the optimum receiver is the minimum distance receiver, of course, if all the a priori probabilities are equal. So if all the a priori probabilities are equal, then the optimum receiver is the minimum distance receiver. So you choose MI if the distance between the received signal with the ith signal is less than the distance between the received signal and any other signal denoted by J that are not equal to I. So so in case of QPSK also you saw that this rule applies. So this is the more general form, and if you have a n dimensional space, then this is the general formula for the distance of the ith signal from the received signal, where both the ith signal and the received signal has k components, and k is equal to 1 to n for an n dimensional space. For a 2 dimensional space, this k will be from 1 to 2. Okay. For a 3 dimensional space, it will be k equal to 1 to 3, etc. Okay. So so now let's see some examples of MRE signaling. So first is the MRE amplitude shift keying. Okay. Sometimes it is also called MRE, coherent amplitude shift keying. The reason why it is called coherent is because all the signals, all the M signals are generated from the same source. So that's why they are coherent in nature. Okay. So, so the transmitted signal is denoted as SIT. So this is a signal modulated by this cosine waveform. So where Fc is the carrier frequency, but since only the amplitude is varying with I, so each signal, ith signal has a different amplitude denoted by Vi. Everything else is same. Okay, so so this is ASK in nature, and you have M such signals. So I is running from 1 to M. Okay, so that's why it's MRE, amplitude shift keying. And the amplitude, so this term, this cosine 2 pi fct and then square root of 2 over s in front, this entire term can be denoted as a basis function phi 1t. And only the amplitude is varying, and that is denoted as I minus 1 times delta. Okay. So basically this MREASK can be represented with only one basis functions, and the signals. So for I equal to 1, if you put I equal to 1 here, it will be 0. So the first signal is 0. Then the second signal is at a distance delta from the first signal, because if you put I equal to 2 here, then your S2t is nothing but delta times phi 1t. Okay, and delta times phi 1t means your S2, the phi 1 component of your S2 is delta, and S2 doesn't have any phi 2 component, so the signal S2 is along the phi 1 axis. Similarly, S3 is twice delta, and so on until Sm, which is m minus 1 times delta. Okay, so these are the M signals all lying across the phi 1 axis. Okay, and this is an example of MRE ASK. So the receiver for this type of MRE ASK is simple. So you have the ith signal, and the noise is added, so you receive the signal RT, that is the signal SIT plus noise, and then you correlate it with phi 1, integrate and take samples every kts seconds. Okay, so you will get the component R1 of the received signal vector, and then you put it through a decision device and recover the original signals and the corresponding messages. Okay, so now what will be the decision device? So what is the decision rule here? Okay. So the decision rule is simple. So let's say you have this M signals. So here is your S1t, which is 0. This is S2t, and so on. And this one is your SMT. Okay. So so if you draw the conditional PDFs, which are normal distributions like this. So this is the conditional PDF of the received signal given S1. This is the conditional PDF of the received signal given S2t. So on. So all these are the conditional PDFs. So this is the conditional PDF of the received signal given SKT. And since everything is one dimensional, so it's all across the phi 1 direction, so you only have one dimension for the received signal. So you can write the conditional PDFs in terms of the R1 component of the received signal as well. So So these are all the conditional PDFs. Okay. So now, if you look into the two extreme signals, S1T and SMT. So let's look into the S1T first. Okay. So this is 0. This is the origin of the axis, as you saw here. So this was starting from 0. S1T is 0 and it lies here. Okay. And this is at a distance delta. Okay. So that if you just consider S1 and S2, then this is your decision boundary. Okay. If you consider S2 and S3, then your decision boundary will be somewhere here, and so on. So the decision boundaries between any two pairwise signals is the perpendicular bisector between the line joining the two signals. Okay. So these are all the decision boundaries. So now if you look for just S1, okay. So this is the region for S1, okay. Whatever is falling this side is for S1. So if your receive signal falls in this side, then you choose S1T. Okay. So in other words, the decision boundary starts at a distance delta by 2. Okay. So this is 0, this is delta, this is exactly halfway between these two. So this starts at delta by 2. Okay. So essentially, if your received signals component R1 is less than delta by 2, which is any point towards this direction, then you choose S1T. So the decision rule for S1T is that if your R1 is less than delta by 2, you choose S1T. Okay. For SMT, let's see. So this is this signal stays at m minus 1 delta. So this is the coordinate. Okay. If you go back, so this SMT lies at m minus 1 delta. Okay. And this distance by symmetry is delta by 2. Okay. So this distance, this decision boundary lies at a distance m minus 1 delta minus delta by 2. So this is basically m minus 3 by 2 delta. Okay. So the decision boundary, this extreme decision boundary lies at this much distance from the origin. Okay. So now if your received signal falls anywhere towards this side of the decision boundary, then you choose SMT, and by this geometry, this is nothing but R1 greater than m minus 3 by 2 delta. Okay. So if your R1 is greater than m minus 3 by 2 delta, you choose SMT. Okay. And for any other SKT which is in between, the decision rule is basically this. So this, for any k, the kth signal lies at k minus 1 delta, and it is surrounded by two decision boundaries. Okay, in two sides. Okay, one is for the k minus 1th signal and the other for the k plus 1th signal. Okay, so this decision boundary is at a distance k minus 1 delta plus k minus 1 delta plus delta by 2, and this decision boundary is at a distance k minus 1 delta minus delta by 2. So if you simplify these two values, then this is basically between k minus 3 by 2 delta and k minus half delta. So for any other k between 2 to m minus 1, if your received signal component falls between these two values, then you choose SK. So if your received signal falls here, which is between k minus 3 by 2 delta and k minus half delta, then you take a decision in favor of sk. So this is the decision rule. So this is the optimum decision rule, and is uh, that is taken care of by this decision device in the receiver implementation. So now if you want to calculate the error performance of MASK, then what should we do? So basically the probability of error is the sum of these terms. So this is basically nothing but the error due to each of these signals multiplied by the a priori probability of those signals, and then you do the sum of I from 1 to m. Okay. So so for any signal that is other than the first signal and the extreme mth signal, your probability of error is basically, so consider any signal, kth signal, where k is between 2 to m minus 1. Okay. So for such case, the probability of error is the sum of these two shaded areas. Okay. Because this is the region of the kth signal, and if your received signal falls beyond this, okay, then you are having an error. Okay. So that means if you integrate the PDF of the received signal given SKT was transmitted beyond this limit of the decision boundaries, which is these two shaded areas, this one and this one, then you get the probability of error due to SKT, where k is from 2 to m minus 1. Okay. And these two areas, if you go back to the lecture where we discussed the Q function for the first time, you will probably see that these two areas are nothing but the Q function of this term. Okay. So this area is basically the integration of this PDF, integration of R1 given SK T from minus infinity to this value. Okay. And this value is k minus 3 by 2 delta. Okay. And this area is the same integration from k minus half delta to plus infinity. Okay. So because the limits are between k minus half and k minus 3 by 2. So this, okay. So essentially you are doing this integration, and if you replace the PDF, which are normal distributions, okay, with the mean SK S1K, okay, then you will find that each of this area is equal to Q function of delta over square root of twice n0. Okay, both are same, which is equal to this. Okay, and if you add them, then the error due to the ith signal, where I is 2 to m minus 1, is basically 2 times the Q of this term. And for the extreme signals, for the first signal and the mth signal, you have only one area to add, because if you look here, for the first signal, the probability of error is this area. For the mth signal, the probability of error is this area. So this area, which is always equal to q of um, delta over square root of 2 and 0, will give you this value for I equal to 1 to n. Okay. So now if you add all these terms according to this equation and simplify them, then you will get that the probability of error for mask is 2 times m minus 1 over m into q function of this term. Okay. So now you can see, so far what we did, the maximum amplitude of the transmitted signal is m minus 1 delta. So that is the amplitude of the signal SMT. Okay. So basically you have a set of signal with from S1, S2, S3 up to Sm. Okay. So MRE-ASK, okay, sends these M signals. Okay. So let's assume that your M equal to 4. Okay. So basically M equal to 4 means this is 2 to the power lambda. So lambda equal to 2 here. Okay. So basically you have 2 bits per symbol and you can arrange them in these 4 possible ways. Okay. And whenever you have these combinations, you are sending the 4 signals S1, S2, S3, S4. Okay. And your S1 is, let's say, 0, your S2 is delta, your S3 is twice delta, and S4 is 3 delta. Okay, according to the previous rule. Okay, here I minus 1 delta. Okay. So whatever is the combination of your bits, okay, you are sending either nothing or some or S2 or S3 or S4. So let's say my bit combinations are like this. Let's imagine that I have 1, 0, okay, let's say another 0, then 1, 1, 0, 1, like this. Okay, so these are my bit combinations of the original signal. Okay, so let's say I am counting 2 bits at a time. So if I have 1, 0, then the pattern is S3, and S3 is twice delta. Okay, so when I have 1, 0, I am sending a signal, the cosine signal. Okay, let's do this in a fresh page. Okay, so let's say I have this pattern 0, 0 is S0, sorry, S1, and S1T is 0. For 0, 1 I am sending S2T, and that is equal to delta. For 1, 0 I am sending S3T, and that is equal to twice delta. And for 1, 1 I am sending S4T, and that is equal to thrice delta. So this is basically MRE-ASK. Okay, and sorry, S1T is 0, that is fine, but S2T is not just delta. Delta is the amplitude, but then you have a term here that is square root of 2 over TS, let's say, yeah, square root of 2 over TS cosine of 2 pi FCT. So and this all of them has the same parts, right? Okay, so let's now see what happens when you have a bit pattern, like let's say 1 0 0 1 1 0 1 0 0 1 1 0, let's say. Okay, so so this is like, let's say this looks like this roughly. Okay, so now if I'm looking at 2 bits at a time, because we are having m equal to 4 here, so 1 0 means I have s3t. So during this duration I will send s3t, which is a cosine function of amplitude. Let's say this is, the amplitude is between plus and minus twice delta. Okay, so this is my s3. Now I have 0 1. So when I have 0 1, I am sending s2, which is again a same cosine function, but the amplitude is less. Okay, the amplitude is delta, half of that. So I have plus delta and minus delta. So the amplitude here is like this. Okay, between minus delta and plus delta. Now when I have 1 0, I am sending again s3, so I will be doing this. The frequency remains the same. Okay, fct is same. Again I have a 1 0, so I will send again this same amplitude cosine signal. Now I have 0 1, so I will send the smaller one, and then I have 1 0, then I will send the larger one. Okay, and let's imagine I have 1 1 here. This pattern was missing, so I have 1 1. So for this I have this signal, so which is between, let's say, plus 3 delta to minus 3 delta. So I have the largest amplitude for this particular pattern. So the point is that at any point of time, the maximum amplitude of the MRE ASK signal is 3 delta for m equal to 4, and generally speaking it's m minus 1 times delta. Okay, so that is what is mentioned here in this slide. So the maximum amplitude of the transmitted signal is is m minus 1 delta. So the maximum transmitted energy is m minus 1 delta whole square. Okay, because energy is the amplitude square, and the maximum average transmitted energies can be reduced without any sacrifice in error probability by changing the signal set to 1, which includes the negative version of each signal. So instead of starting everything from 0, okay, so this is, earlier this was your S1, this one is S2, S3 and so on. So this was 0, this was delta, this one was twice delta and so on. So instead of doing that, you just shift the axis in such a way that you have a symmetrical representation. So now you have all the signals at a distance delta. The distance between each of the signal still remains delta, But now half of the signals are having negative amplitude and half of them have positive amplitude. So, so in that case, okay, what will happen is that the maximum transmitted energy of the new signal will be this, okay, and the average transmitted energy will be reduced too. And the error probability will remain the same, because the error probability, as you may recall, just depends on the relative distance between the two signals. So the relative distance still remains delta, okay. So the error probability won't change, okay. Um, so we have used this concept before also, when we were rotating the axis, and we were getting a scenario where we can use only one matched filter in case of the um, binary transmission. So so this is also similar concept. So when you change or shift or rotate the signal space, then the energy or the average energy of the signals, that changes, but the error performance remains the same, because the relative position of the signals with respect to each other remains the same, okay. So now, talking about error probability, so the error probability should be calculated in terms of EB by N0, okay, where EB is the average transmitted energy per bit, okay. So, so in case of your MRE signaling, you define symbol energy by ES, average symbol energy, okay. So this is the average transmitted energy per message or per symbol, okay. So, so this is denoted as ES, and that is the energy of all the signals added together and divided by M. So basically you are taking the average of all the energies that each signal contributes. And according to this, the new representation where you are shifting the axis, the amplitude of the ith signal is given by this term, okay. So you are taking the square of that, and then you have this expression. And if you expand this and sum over all I, okay, applying the rules of basic number addition, so addition of a series of numbers, you can find that this term is m square minus 1 times delta square over 12, okay. So this you can do. So if you just expand this term, so this will be 4i square. So basically you are summing the square of the first m terms, okay. So the first addition will be like this. So this is basically 4 times this, and this identity you know from your basic math classes, okay. So this is basically 4 into I twice I plus 1 by 3, I guess. I have to look up myself. So basically this is the identity that I'm trying to use. I think I'm right, but just cross check, okay. So you apply this for the first term. For the constant term, it will be just m. For the other cross terms, if you have just I, then you have to apply this identity, which is, So if you apply all this here, then you will get this term, and simplify, you will get this m square minus 1 times delta square by 12. Okay. So now what is your EB? So this is your ES, which is the symbol energy, average symbol energy. So average bit energy is simply average symbol energy divided by the total number of bits in each symbol, and that is given by log 2m. So basically, if you have lambda number of bits per symbol, then your m is 2 to the power lambda. So therefore your lambda is log 2 by n. So ES is EB is basically ES divided by lambda, which is ES divided by log 2m. Okay, so this turns out to be this expression. So from here you can write delta in terms of EB. Okay, so delta is written in terms of m and EB. So now you saw that the probability of error that you calculated few slides back here is this. So now I will just replace the value of delta by this value which we just obtained, and we can write the probability of error in terms of just m and EB by n0. Okay, and probability of bit error is 1 over lambda times the probability of symbol error, and lambda is nothing but log 2m. So this simplifies to this final expression. So this is the probability of bit error, and this is the probability of symbol error for MRE ASK. Okay, and if you plot the probability of symbol error with EB by n0, then you can see that as your m increases, okay, your error performance gets degraded. Okay, you are gaining over bandwidth. So for m equal to 2, your bandwidth is 1 over TB. For m equal to 4, your bandwidth is 1 over 2 TB. So whatever you are transmitting, whatever information you are transmitting within a bandwidth of 1 over TB by having m equal to 2, the same information you can transmit using half that bandwidth if you use m equal to 4, and this increases. This advantage over bandwidth increases. So you can transmit the same information within 1/3 of the bandwidth if you have m equal to 8, and 1/4 of that bandwidth if you have m equal to 16. So you are gaining in terms of bandwidth. Okay, so gaining in terms of but let's look at the error performance. So for error performance, I think you are losing. And why this is so? So probability of error. So let's look here. Okay, so let's say if I want to achieve a probability of symbol error of 10 to the power minus 6. Okay, so the EB by n0 for m equal to 2 to achieve a 10 to the power minus 6 probability of error is roughly 11 dB. Okay, the same thing for, let's say, m equal to 4 is roughly 14 dB. Okay, so you have to expend 3 dB more power. So this means 3 dB more power is required to achieve a probability of symbol error of same 10 minus 6 with m equal to 4, and this thing degrades as we increase m. So for m equal to 16, you are probably using about 23, roughly 23 dB of power, like EB by N0 has to be 23 EB. So let's imagine that the noise remains the same. So what you are achieving with 11 dB for m equal to 2 is achieved using 23 dB. So that is actually 12 dB more. So 12 dB more means it's basically 10 to the power um, 12 by 10. Okay, so this, so almost more than 10 times. Okay, more than 10 times power, signal power you have to expend to get the same probability of error as m equal to 2. Okay, if you are using m equal to 16. So this is bad in terms of the probability of error performance. Okay, so you are gaining in terms of bandwidth, but you are paying a price in terms of your receiver performance. Okay, so I'll stop here today, and I will resume in the next video lecture. Thank you.